that's how we all learn, I guess. So now that Matthias has done the easy part, I'm gonna do the hard part. No, it's not gonna be like that, but it's gonna look at the core plugs again that Matthias was talking about half an hour ago, but a little bit with more detail, and the core plug or the studies that we're currently doing with the ERC, we have proposed a slight revision to their experiments, and we're testing that out. As Matthias said, right now, actually, the experiments are being conducted as we speak. So gas huff and puff on core plugs. So why do we do this? As Matthias has mentioned, it's all about trying to understand how the recovery efficiency, or put it differently, if there is a shattered volume, what can we expect from it in terms of recovery from doing the huff and puff process? And a key indicator of how these rock pieces, rubble, whatever you want to call it, debris, if you will, how those behave with the fluid system, the injection gas of your choice, etc., can be done through these fairly simple core experiments. You can get some ideas about it, and actually also you can history match these core models or these core experiments to tune your shattered volume part of the reservoir, and we'll get back to the process of that. So what has been the standard, and there's many papers, Hawthorne et al. 2017 is one of them, there's many, shows how the ERC normally goes about when they do these core experiments. So they have essentially, this sketch is not to scale, but what they do is they put a core into a core holder. They pressurize it to 5,000 pounds or sometimes 6,000 pounds. They keep it at 230 degrees, not C, but Fahrenheit. And then they flush the core at a constant pressure every hour. So they maintain the pressure at 5,000 pounds. They just bleed out the injection gas by putting in new injection gas. It's there's probably a couple of psi pressure drop during that bleeding, but it's essentially just keeping the core holder at 5,000 pounds and 200 degrees Fahrenheit, and then you shut it in for, I think it's 50 minutes, and then they bleed it for 10 minutes, putting in fresh injection gas, and then diffusion does its thing for 50 minutes, and then so forth. And then they do one overnight. That's the last point you see in these plots. So that's what they've been doing. So there's no pressure cycling in these experiments. It's just constant pressure. And what you're essentially relying on here is diffusion, compositional differences, if you will. Yeah, so the soaking was performed for 24 hours at constant temperature pressure, like I said. Okay, and this is the result. So here they show, this is one of the plots, and here they show for given core. I'm guessing most of these cores that are documented in the literature are from Bakken. And what they commonly do is, let me just get a laser pointer there. So what they commonly do is they have a middle Bakken core. That's the target volume in Bakken. And then you have the upper Bakken and lower Bakken, which are shales that are not considered target. But they also do experiments on one of those benches as well to compare recovery efficiencies for different permeabilities. The middle Bakken is higher permeability. So this is most likely a middle Bakken core. They always obtain more or less 100% recovery. And you see that nitrogen gas is actually quite an inefficient gas. It only gives about 25% after 24 hours. Whereas compared to CO2 and ethane, which are very efficient gases. And they've also done a 15% ethane-methane mixture and pure methane. So so what you can take away here is that CO2 is a little bit special. It behaves differently from hydrocarbon gases. But what you can take away is that the richer the gas, the injection gas is, the more efficient it's going to be. So methane is called the most lean, or nitrogen is actually the most lean gas, but methane is the most lean hydrocarbon gas, and ethane is richer, and then comes propane, I think, and so forth, and then butane. And if you start to go higher than that, you will essentially start to putting, if you process the injection gas, you get oil, which is that's something we're going to get back to, but it's something to be aware of, actually. Okay, so what happened? The reason the recovery is like it is because the dimension here is so small. Remember, we argued, or Matthias argued, that it's the minimum dimension that matters, which for these cores are around 11 millimeters. So then that means that it's 5.5 millimeters to the center of this core. So for 24 hours, diffusion, the speed of diffusion is able to mix within those 50 minutes of soaking, if you will. Diffusion is able to permeate and mix with the entire core. So this becomes very similar to the PVT experiment, because you obtain full mixture, or a complete mixture, between these bleed cycles, if you will. And that's what we're trying to get at here, is essentially, this is from the, I don't have a writer as Matthias does, so I'm just going to point and tell. But what Matthias is trying to go at here, this is from the 2019 ERTEC paper, where we're just taking the plot from Hawthorne 2017 and comparing it to the PVT experiment for the same gases. And you can clearly see that although the axes are different, here it's time, here it's moles injected, but the shape is very similar, and it behaves very similarly for the different gases. Okay, and then there's pressure above the MnP first contact and below the MnP first contact, which gives you a break, turning it from swelling to vaporization. Whereas in this case, the injection pressure is higher, so you get a swelling process. Matthias, you want to comment more on this plot, or?
Yeah. So there's a few things to mention here. The main thing that we wanted to demonstrate is that the scale of these core plugs is essentially so small that it is a diffusion. It will mix through diffusion so quickly because of the scale, that it is essentially the same, or directly analogous to a PVT experiment. And this PVT experiment that we look at here is just a constant volume injection, or a constant volume depletion experiment, whatever you would like to call it, that is done at a constant pressure, which is what's the case for this core plug to the or responsibles to the left, and that's what we've simulated with the CVD experiment there to the right. There's a few other differences here. One is related to the experiments to the right. They're done with on our live reservoir oil in the PVT cell, while the experiments that we actually found out later, these plugs to the left, is done with a stock tank oil, actually. And as you'll see, the efficiency to the left is higher in terms of at least absolute numbers there than to the right, and that's most likely due to the fact that they're using stock tank oils, because as we know, at least on stock tank conditions, the saturation pressures of a stock tank oil is stock tank conditions, which means that if you inject, you'll essentially get a very, that swelling mechanism will be dominant from the first PSI, and you don't actually have to wait until you're above a saturation pressure of 2,000-3,000 PSI for that to be the case. So there's a few small differences like that, but directionally they're showing the exact same trend. That's also why the vaporization, nitrogen is essentially flattening off. That's what you see in the experiment as well. You see both the mixture of ethane and methane and pure pure methane is with the exact same trend, and they're also showing this difference from a very high recovery efficiency to something that's lower, which is where they switch to become a more vaporization-driven process.
Yeah, thank you. Yeah, so that's just the same plot, bigger. So probably some of the things Matthias says here is just said is summarized here. I'm not going to go through that in detail. So what we have proposed for ERC, and they actually have done an experiment on it already. I think it's published in the Fuels Journal, if I remember correctly, is to do recovery experiments on different sized core plugs. And the reason we advocate for that is because it is unlikely that this shattered volume will have an homogeneous distribution of minimum dimensions. There's going to be large pieces, small pieces, and everything in between, most likely. And so it would be interesting to know, okay, how does these pieces perform with size? Okay, what if you inject for 30 days? Which of them will you obtain full and complete mixing within, and which of them will only be partially mixed within that time frame? And of course, all the other operational considerations, pressure and injection gas and so forth. So this is from that paper. So what we can see here is that. So we've made a drawing here just to clarify what these that this legend refers to. So it's a middle bucking core, and the largest one is this standard plug that they use. It's about 11.2 millimeters in diameter and 30 to 40 millimeters high. It depends. And then what the ERC do is they chop these plugs into coins, they call it. And the interesting or the important thing to note here is that the minimum dimension for this piece is the 11.2. It's the radial dimension. But for this piece, it's not the radial dimension, it's the height that becomes the minimum dimension. So the minimum dimension here is 1 to 3 millimeters, and the minimum dimension here is 11 millimeters. Or you could use the convention of using half of this, since the injection gas only has to travel into the center of the core to mix with everything. But as long as you stick to one convention, it doesn't matter. So what you can see here is that if you look at a point in time before you reach 100% recovery, then you can see the difference between the blue one is a coin, and this green one, I think it is this rod. So we're comparing those two. And what you can see is you can translate this into a plot that of recovery factor versus minimum dimension, LM. And then, of course, since you only have 2 points, it's very hard to interpolate with any higher degree of accuracy than a linear interpolation. But if you interpolate it with different functions, just standard functions, you can get an idea of how this is going to look for larger dimensions. Okay, when does it approach 0, and so forth. So, but no matter what this graph looks in reality, the point here is, as with other aspects in life, is that size matters. It does matter how big these pieces are for recovery factor within a given time frame. For an injection period of 30 days, it's going to matter how big your rock pieces are. The bigger they are, the less they recover within those 30 days. That's what this plot is trying to tell you.
Yeah, and just a note there, Stian. So here, it's a little bit hand waving. This is based on experimental results. We only have to call it data points to I guess make this distribution of at what scale does the recovery efficiency or recovery factor essentially become 0. But what Stian has documented in this paper that was also provided, and we'll go through that plot later in the presentation, right, Stian, is that probably around somewhere between 8 to 10 feet, like recovery by diffusion. If your rock or the minimum dimensions are that big, then the potential for huff and puff recovery goes to very close to zero, essentially.
Yeah, and in terms of this plot, that looks optimistic. I mean, this is a meter. 1 meter is 3 feet, so it's going to be even outside of that. But you know, again, this is just us putting some equations between 2 points. There's no saying that this is completely true. It's the point here is that it does matter what the dimension, the minimum dimension, the magnitude of the minimum dimension matters. Okay, so the experimental objective that we proposed for ERC is, first of all, the point is to understand how gas huff and puff recovery is affected by the following, and is the different rock plug sizes we just mentioned. We have also proposed to do a pressure cycling experiment, as opposed to the standard way they're doing, which is this constant pressure. That's only going to give you, except for the first initial pressurization, it's going to be a completely diffusion-driven process. But if you do the cycling, you also get the Darcy flow, or the convection part of it, if you will, or advection. And then also try different permeabilities. So I think the course that they're testing again is Bakken course. The experiments they're here. So they're going to do some tests on the middle Bakken, which is the high perm in the relative sense, and then I can't remember if it was the upper or lower, but they're going to do different lithologies to get the permeability effect as well. And the point there is to sample as much data as possible, gather as much data as possible, such that it's possible for us to do a modeling of that experiment, or of those experiments. There's going to be many, and try to see, can we, in one way or another, do it just by reservoir simulation, including diffusion, can we represent or history match these results? And the point there with that exercise is that the outcome of that will give you a set of tuned diffusion coefficients for that fluid system. And also it will give you, okay, if you have this size distribution of minimum dimensions in your shattered volume, you can populate that in your reservoir model. We'll get back to how, and then get at least we believe, a better estimate of the huff and puff performance. That's at least the thought. Okay, so that's what it says there. So the objective of the modeling study is to quantify key physical parameters, diffusion coefficients, relative permeability curves, capillary pressure, and the intention of gathering all this is to use it in upscaling from lab to lab scale to well scale or field scale. Okay, so the experiments that we proposed are going to be something like this. So we're going to have one plug where the minimum dimension is the height, and then we're going to have 2 plugs where the diameter is different, meaning that the L-min is D2 here and D3 there. So we're going to do injection, then production, and hopefully the results our thoughts, or what we're hypothesizing, is that the results will look something like this. So the smallest dimension will give the highest recovery, and the distribution of recovery will follow the increase in minimum dimension. So this is versus time, and plotted against gas injected, it will look something like this. Simply, yeah. And again, these experiments are, because of the complete mixing that it most likely is happening, you see that from the recovery profiles that there has to be some mixing going on here. We believe that the PVT experiment is quite analogous to that. But again, assuming this PVT experiment assumes complete mixing. Okay, so now turning a little bit over to something that doesn't have anything to do with the core experiment specifically, but it has to do with why are we doing core experiments. And the example, or for the industry right now, of what this shattered volume, stimulated rock volume, whatever you want to call it, what it looks like is this sampling and I should say NSRE study. This an Eagle, for example, which was done by ConocoPhillips, and it's by Raderman and a bunch of other guys. Helen, I can't remember the name.
Helen Pearl.
Thank you, Matthias. So these plots here are essentially showing that after they drilled the well and they fracked it, they have drilled a bunch of wells through the shattered volume, if you will, so very close to the well they fracked, and they've cored the entire thing. And what they're doing here is they're counting fractures per 50 feet in those cores. And these are just S3, these are just wells, different wells. You can read the paper and you'll get they have a drawing of how the wells are configured. But what you can see here is that per 50 feet, some of the places here, you have an extreme amount of fractures. Here you have 50 feet, here's 50 fractures per 50 feet. It's a 1 foot fracture spacing. So they're definitely doing something to the rock. And whether it's shattering it completely or just generating a bunch of hydraulic planar fractures very close together, who knows? But at least it seems like these guys in ConocoPhillips, they believe that the stress field is controlling the growth of the hydraulic fractures, and then it's only planar fractures, but they're very, very close together, very dense. And then you can ask yourself, is that bad for huff and puff? No, not necessarily, because if these fractures are very close together, that means that you have a very small minimum dimension. If there is 50 fractures here one fracture per foot, then you have 1 foot between each fracture. So even though these fractures are, say, 300 feet long, there's only 1 foot between them. So the minimum dimension here is 1 foot. So even though it's not shattered like the picture we showed you earlier, where the fractures go everywhere and it's just loose pieces of rock, this still can be a very good environment for huff and puff. If this example here represents each and every unconventional well in North America, that's of course an assumption. But I think in the Eagle Ford there's a very strong stress field, and yeah, there are assumptions there. Again, neither me nor Matthias is an expert in geomechanics, but so this is just very heavy in text. But the point here is that you can read this yourself. But it's just what I said is that the key takeaway from that paper in terms of EOR is that the shattered volume might not look the exact way that was proposed by Curtis at a forum in 2017, with this almost like if you break a mirror, it's just pieces everywhere, but more like very, very densely spaced hydraulic fractures. I think we actually have a picture of that later on. So, and here are some very, very expensive papers. So again, this sampling the SRV paper cost about $30 million. It says Urtech here. It was actually published in the SP journal as well, so there is a journal version of it as well that you can obtain. And there are some other ones. They had a follow-up paper also, which is this one, analysis of the drained rock volume, and a couple of other papers. These are definitely worth reading if you're interested in seeing, just observing what the nature tells us. I mean, you can, whether the lines that these guys draw in their figures or these guys are right or wrong, doesn't matter. Just look through all the interpretations and just observe what they're showing. I mean, here they're just counting fractures, so that can't be too off, right? And then you can make your own opinion about whether this is right or wrong and what it tells us.
The nice thing about it, Stian, this is real data. You can actually go in there. They have images of the spacings here, and I assume that most of the people on the call have read these papers. because it's probably the papers that I heard the most talk about, at least when I discuss Zurich papers. And the nice is some actual measurements of field dimensions of these dimensions that is important for huff and puff. And we said now that, you know, through the work that Stian has done, this you know, the fusion and the ability of obtaining enhanced oil recovery from gas huff and puff kind of diminishes at dimensions probably between 8 to 10 feet, at least if you use kind of published diffusion coefficients and whatnot. So here, if you have 1 feet in minimum dimension, and that's something you actually have systematically, not only the Eagle Ford. I mean, the hydraulic test size is given very, very consistent results as well in the Permian. So if that's true in general, then there's a lot of potential for gas huff and puff in these plays from that perspective, at least.
Okay, so that was the section about core plugs and why they can be interesting and why experiments on those plugs can be of interest. So now this next session is going to be